Hey guys, what's up? My name is Gabe and this is Games with Gabe. This is the next episode in the Coding a 2D Physics Engine in Java series. In this episode, what we're going to be doing over is line versus Box2D and line versus AABB. So how to tell if line is intersecting with a box that's aligned on the axes, and how to tell if a line is intersected with a rotated box. Okay, so this one's quite dense, but we're going to go through it step by step and see how it all works. So let's check out the math first. So box versus line. I'm not gonna lie to you guys, I recorded this once, but my explanation was so horrible, I was like, I need to re-record this so that I can actually explain what's really going on. I missed a lot of the stuff. But this is a pretty complicated topic. You would think checking whether a box is intersecting with a line shouldn't be too difficult. Like when we look at this, we can very easily see, yeah, this is totally intersecting, but it's difficult to conceptualize mathematically. It's difficult to say with certainty and fast how this is intersecting, to come up with a fast method. So let's break it down to its bare essentials, right? Basically, what we want to do is we want to say, hey, we know there are 2 points of intersection if a line is intersecting with a box. There will always be at most 2 points, okay? One of the points might be inside the box. Say you had a line like this, and we're talking about line segments too. You would still have 2 points. You would have the point of entry and the point that it resides inside the box, or like this case right here, you would have the point of entry and the point of exit. So 2 points, we should be able to find them every single time. How you do that? How the heck do you do that though? That's difficult. It's really difficult. I'm just gonna jump right into the mathematics of how it works though, because I think that's the easiest way to explain it. Okay, so what we should do mathematically is, first of all, we draw a line from this point to the maximum of the box, which would be the top right corner, and this point to the minimum of the box, which would be the bottom left corner. These two vectors are very important because they're sort of the vectors that tell us what's going on. They're the maximum and the minimum bounds of the box, and those are the bounds we're going to have to check. Now, I'm going to show you visually exactly how this is going to work, exactly how we will figure out where the intersections are happening. So visually, how do we know where the line intersects with the box? Well, there's 4 sides of the box, right? We have side 1, side 2, side 3, side 4. What we want to do is we just want to check and see if the line, what point of the line is closest to that edge of the box, right? So we would check this x coordinate, we would check this y coordinate of the line, what x coordinate is there, and we know the line's equation looks something like this, right? So theoretically, one of the ways we could do this is we could say, okay, check the box's max x. This would be this line right here. And if we plug in that x, we'll get a y. That y would be this point right here. Then we would say, okay, plug in this guy's y, so the max y, or that would be the min y, right? And so then we would plug that in here, and then we would find x. And that x would give us this coordinate right here. We could do that, and then if we continue down the line, then we would get a point somewhere down here for this side, and once again, and then for up here, we would get a point actually somewhere all the way out here, way up here. But that's not quite the best way to do this because that takes up quite a bit of time to do, and it's a little bit hard for the computer to do. So what we can do instead is sort of figure out the distance along the line that these points lie, right? So we could say, okay, well, this point is approximately 3 units in the direction of this line, and this point is approximately 3 plus like 2 units in the direction of this line. And this is sort of how we're going to be doing raycasting too, right? We march in the direction of the line, right? And then we basically check, is the length from here to here less than the length of our line segment? If it is, then we have a successful intersection. So how do we do that? Well, it's kind of weird, but it's also not too hard. So what we do is, let's work out this concrete example, okay? So this is our vector. We're going to say this is vector A, and then we'll call this vector B, which is our line segment. So vector A looks something like, if we take the vector, that's 8 minus 3, which is 5, 8 minus negative 2, which is 10. Okay, so that's our vector A. What about our vector B? So vector B, which is our actual line segment here, well, that's just 11 minus 3, which is 8, and 4 minus negative 2, which is 6. Well, that's pretty nice. Now, first step we're going to want to do is we're going to find out what direction is this vector pointing in. What direction is that pointing in? And we'll have to do a square root for this, but that's fine because we're performing a raycast and it's expected that this will be a little bit more expensive. So To find out what direction this is in, we normalize the vector. How do we do that? First, we get the magnitude of b. So magnitude of b is just the square root of 6 squared plus 8 squared. That's just the square root of 36 plus 64, which is 100. Square root of 100 is 10. Okay? Simple. Next, to turn that into a unit vector, I'll call u. We just divide 8, 6 by 10, by its length, right? This will give us the vector 0.8, or 4/5, 0.6, which is just 3/5. So what this tells us is we have a vector that looks something like this. It's very small, pointing in this direction. This is our unit vector, the direction of our line. Now, to figure out the distance along the line that we intersect with this point is actually pretty easy. We just take our x component of a divided by our x component of the normal. So we'll just say ay over uy, which just gives us 5 over 4/5, which we know is just 5 times 5/4 because of math. And this is just 25/4, which we can reduce further to 6.25. Now, what is this number 6.25? That number is the amount of units in this direction that we would go to intersect with this point, okay? We can verify this too. If you want to verify it, how do you verify that that's true? Well, we first have to find the line equation, okay? I'm going to erase all this real quick. This is true. We know this is true. Okay, so let's do the line equation very quickly. Y equals mx plus b, okay? We know what m is, right? M is this. This is the delta x and delta y, which is just 6/8, right? So dy over dx, which is just divide by 2, that's 3/4. So y equals 3/4 x plus b. Let's plug in an x and a y. We'll plug in this x and this y, okay? So that's 4 equals 33/4 plus b. Let's find what b is. That would be b equals 4 times 4 is 16 over 4 minus 33 over 4, which is just negative 17/4. So line equation of y equals 3/4 x minus 17/4. That's our line equation. How does this help us? It helps us because now we can just plug in this line. So let's plug in, this is 5 units to the right of this coordinate, right? So that would be 4, 5, 6, 7, 8. So 8. Let's say y equals 3/4 times 8 minus 17/4. What does this equal? Well, 3 times 4 is 24. 24 minus 17 is 7. 7/4 is 1.75. Okay, so we have at 5, 1.75, or not 5, but this is actually 8. 1.75 is where this point is. So this point is at 8, 1.75. Now, let's do one more thing, okay? So we know our line is going in this direction, right? So if we want to go 6.25 units this direction, all we have to do is scale it, which means we just say 6.25 times, and we'll do 4/5 and 3/5. And let's actually change this back to fractional form because that's a little bit nicer. So that's just 25/4 times 4/5 and 3/5. Well, 25 divided by 5 is just 5. So that's 5 times 4 is 20 over 4, and 5 times 3 is 15 over 4. Well, what is that? That's just 5, comma, 15 divided by 4 is 3.75. Well, what does this mean? This means if we go 5 units to the right of this, 3.75 units up from this start point, we will hit this coordinate. And that is true. If we go 1, 2, 3, 4, 5 right, and 1, 2, 3.75 up, we hit that coordinate exactly. Okay, so now we know that this is true. We know that we can very easily solve for the length of from the start of the line to the point where it intersects with the box, literally just by dividing this a, so its vector, the maximum vector, by its unit directions component. So doing that will give us the length. So then we could do the same thing. So this is the y component. So this is max y, right? Which would be something up here. So then the point's going to end up being somewhere like actually out here, because if we extend this line, it would end up here. So if we do that, if we do ay over uy, and I wrote ay over ui here, this is actually x. This is ax over ux. Ignore that. So AY over UI is 10 over 3/5, which is just the same as 10 times 5/3. 10 times 5 is 50 over 3, which is just, this is just 16 with 2 left over, 16 2/3, which is just 16.6 repeating. Okay, so what that tells us is if we go 16.6 repeating units in this direction, we will end up here eventually. Let's do the same thing with our minimum now. So if we look at our minimum vector, which is actually over here, hasn't been getting any love. Let's check this out real quick. So this minimum vector is at, if we follow coordinates 3, 2, 1, 0, so 0, comma, 0, I think actually, yeah, 0, 0. So if we do 0, 0 minus 3, negative 2, we'll call this vector C, and we can calculate that real quick. C is just, if we look at this, 0 minus 3 is negative 3, and 0 minus negative 2 is positive 2. So negative 3, positive 2 is C. Now let's do Cx over Ux real quick, figure out what that is. Cx is negative 3. Divide that by Ux, which is right here. That's 4/5. We'll multiply by 5/4. That's just negative 3 times 5 is negative 15/4, which we can also denote as negative 3.75. Okay? And these numbers might be wrong. I don't know. Okay, let's do Cy over Uy real quick. I'm not good with math on the fly. Let's do Cy is 2. And Uy is 3/5. We'll divide by 3/5 or multiply by 5/3. Multiply across, that's 10 over 3. That's just 3.3 repeating. Okay, repeating is a bar over the top. Okay, what that tells us is if we were to do Cx, so where's Cx again? That's the min x, which is this point right here. If we were to extend this down, we would eventually hit the line here, which is negative 3.75 units this way on our line. And Cy is this y right here, which means that this point is actually 3.3 units in this direction. So this point is 3.3 units. This point is 6.25 units. This is all really cool, guys, because now we not only know that the line is intersecting, but we can tell its exact entry point and exit point on the box itself. Now, how would we tell if it wasn't intersecting, though? This is all good. It tells us that the line is intersecting, but how do we know it's intersecting? Well, what we would do is we would find the minimum, which we will denote as Tmin, and we'll call this the minimum, and the maximum, which we'll call Tmax, which is this Tmax, okay? And the minimum will actually be the maximum of the minimums, okay? And what I mean by that is we have an AX here and we have a CX here, right? We'll take the maximum and then we have an AY right here and we have a CY. So if we go with our X components, the smaller one of these is negative 3.75. So we'll say the maximum of 3.75, and then we also want to take the smaller one of the y's, which is going to be 3.3, and smaller one of these is 3.3. This is negative 3.75. Okay, so the bigger one is 3.3. So then we can say Tmin equals 3.3, okay? Then Tmax is the minimum of the maximums. So we'll say the minimum of what's the bigger X component. We have 6.25 and we have negative 3.75, well, that's 6.25. And then what's the smaller of the y's, or the bigger of the y's? We have 16.6 and 3.3. Well, that's 3.3. I'm sorry, we're taking the minimum of the maximum. So what's the bigger one? 16.6 is the bigger one. So now the minimum of these is 6.25. That tells us Tmax equals 6.25. which once again is exactly what we expected since it's 6.25 in the direction of the vector. We can tell if the line intersects if Tmin is less than Tmax. That means that this is before this one, right? That makes sense. And if whichever one of these is the bigger one, so if this one or this one, whichever one is farther along the line, if it is not less than 0, right? Because if it's less than 0, it implies it's behind our line segment. And as long as it is less than the length of our line, right? Because if this length, the length from here to here is less than the length of our line, it is still within our line segment. So that's how we will be able to tell. Now that we have all that groundwork, a lot of groundwork, let's code this, okay? And actually, real quick, before we code it, I'm going to go very briefly. Once again, if we have a line that is going something like right here through here, and the box is rotated by theta degrees, we do the exact same thing that we did for the points. We just rotate these points, theta degrees, which would do that, and then rotate this about the box's center, of course. So that would end up somewhere right here. And then we would literally create a new line 2D, create an AABB out of this, and then run the same algorithm for this one, and it will all work out correctly. So if we just rotate the line itself, so that's in the box's local space, then we have the same problem we had just a minute ago. Okay, now let's code those two equations real quick. Actually, coding this is way simpler than that whole explanation. It's super hard to explain exactly how the math works, but you know, you need to know. So we went over it. Okay, so we're going to create a function. We're going to call this line and AABB. We'll say this takes in a line 2D and AABB. We'll call this box. And I'm going to get rid of that P. Okay, so first thing we want to do is check if either of the endpoints are inside the box, because if they are, we can return true early and not do all that stuff I was talking about. So we'll say if the point is in the Box2D, and we'll say the line.get start in the box, or point in Box2D, or actually this is in AABB, and we're going to say line.get end and box, then return true, and this is point in AABB. So we can exit early if either of the endpoints is inside the box, because then we know it's definitely intersecting, okay? Next, what we're going to do is we're going to create that unit vector. So we'll say unit vector equals new vector 2f line.end dot sub line.get start. Okay, and remember, anytime you're doing a modification, wrap it in a new vector. Anytime you're doing a modification, wrap it in a new vector. It will save you from bugs. Okay, and the requirement to create the memory for this is so minimal, it does not matter. It's 2 floats, so don't worry about creating an extra vector 2f. I promise you it'll save you bugs in the long run, and you'll be happy that you did it. Okay, let's normalize this. So we'll say unit vector dot normalize. This way we get this as a normal unit vector. So now it's just pointing in the direction. It's that tiny little vector that we were using. And then what we're going to do is we're going to do this thing to help us catch division by 0 error. So we'll say normal.x equals normal.x, not normal, unit vector.x equals unit vector.x does not equal 0, a 1.0f over unit vector.x, otherwise 0f. And so remember how we were dividing by the unit vector? Well, instead of dividing, we're just going to multiply by 1 over the unit vector, which is the same as dividing. And so to catch against a divide by 0, like if this is a 0, we don't want to divide by 0, so we'll just set it to 0 explicitly if that ever happens. And then we're going to do the same thing for the y. We'll just say unit vector dot y does not equal 0, 1.0f over unit vector dot y, and 0f otherwise. Okay, that part's done. Now let's get the minimum and the maximum of the box and create those vectors min and max, or B and C I think they were in our example. So we'll say min equals box.getMin. We're going to say min.sub local line, or we're just going to say line dot get start dot multiply by the normal, which does exactly what we were talking about, the unit vector. And then we're going to do the same thing for max equals box.getMax, and we're going to say max.sub line.get start dot multiply by the unit vector. And all this is doing is, remember how we were doing like divide by the x and the y of the minimum vector and divide by the x and the y of the maximum vector? Well, that's what we're doing here too. We're just doing it in one step. We're getting the vector, then we're just multiplying by the unit vector, so we multiply the x and the y component all in one go. Okay. Then we're going to find out what the true tmin is. That's the maximum of the minimums. So we'll say math.max, and it's going to be math.min of min.x, max.x, and math.min of the min.y, max.y. We'll do the same thing for our tmax equals the minimum of the maximums. So we'll say math.min, math.max of min.x, max.x, math.max of min.y, max.y. So minimum of the maximums and maximum of the minimums. We now have our true tmin, our true tmax. If tmax is less than 0 or tmin is greater than tmax, this means that we do not have an intersection. We'll return false. And you can look at the equation in the diagram and see how that is true. Then we'll say float t equals, we'll get the bigger t. Tmin is less than 0f, it's Tmax, otherwise it's Tmin. So if one of them is below 0, we just grab the other one to make sure we're checking the highest, the farthest one possible. Then we'll just return t is greater than 0 and t times t is less than the line's length squared. And I did not show you this, but I just implemented this. Just create a public float, length squared. We create a new vector 2f2.subFrom.length squared, gets us the length squared of the line. And that's it. This should be good. Very quickly, let's create a static Boolean line and Box2D. And we're going to take in a line 2D, line and a Box2D, box. We're going to rotate the line into the box's local space and then just run this function again. So literally we're just going to say float theta equals box.getRigidBody.getRotation. We're going to say vector 2f center equals box.getRigidBody.getPosition. And then we're going to say vector 2f local start equals new vector 2f line.start get start. And then we're going to rotate this. Well, actually, let's say vector 2f local end equals new vector 2f line.getEnd. Rotate both of those with our function jmath rotate. We'll say rotate local start around theta and around our center. And make sure theta is negative. We want to make sure we're rotating it negative around our box because that will make sure we rotate the correct direction. And then rotate our local end about theta, about the center. Once again, then we're going to say line 2D, local line equals new line 2D. We're going to give it local start, local end, and then we're going to say AABB, AABB equals new AABB. We're going to give it the min and the max, which is just box.getMin, box.getMax. Then we'll just return point or a line and AABB, and we'll give it the local line and the AABB. Okay, so we just rotate the line into the box's local space here, and then we just construct a new line and a new AABB and return whether those are intersecting. That's all. That's it. We're done. Wow. So that is hard. Okay. In the next tutorial, what we're going to be doing is ray versus primitive tests. So raycasting. It's hard. It's very similar to this though. So if you understood this, great. You're going to understand this too pretty easily because it's very, very similar to what we just did. It's just a little bit different. Actually, we did do a raycast here. So congratulate yourself. This was a raycast. So yeah, we'll talk about that in the next tutorial. If you guys enjoyed this, please hit like and subscribe, and I'll see you there. Thanks.